Physics students, this is Ms. Getz here in Minnesota, and I'm going to start you off on this unit by talking about power production and fossil fuels. So we're going to be thinking about how we produce electrical energy, some other types of energy that we use as well, and I'm going to actually have you start off by pausing the video to look at this graph and jot down what you notice with this graph. So you might have noticed that this graph is showing us how much energy that we're using, the energy consumption in the United States over time, and that it overall is increasing. And so that means that we need to constantly produce more and more energy. And so this unit, we're going to be looking at how we produce those types of energy. You probably already know some different types of energy sources. So if you pause, you can jot down what you know, think back to everything you've learned way back when in middle school, earlier science classes, etc., Bill Nye. So you have probably a few types of energy, and there'll be probably some new ones that you're learning about this unit as well. We'll be talking about non-renewable sources and renewable sources. Today we're starting with thinking about fossil fuels, which are non-renewable, and so this means that they're finite, they'll run out, we won't have them forever, and we can't recreate them ourselves. So fossil fuels include oil and natural gas and coal. And then our other non-renewable source is a nuclear fuel, and that in the United States is uranium. Other countries sometimes use plutonium, but here in the US you reuse uranium. And these are energy sources that once they're gone, we can't use them anymore. And they are storing energy as some form of potential energy. And we can release that potential energy in a couple of different ways. Sources are sources that are not going to run out. These are sources that are powered mostly by the sun, and they include solar energy, so those are solar photovoltaic panels, and active solar heating, which both use direct solar energy to do something energetic in a couple different ways. Other forms also depend on the sun, like wind, which is driven by solar heating of the earth. Wave energy biofuels are a big one. Plants require the sun to grow, and then we can actually take those plants and turn them into some sort of fuel, which is actually a lot like a fossil fuel, except it's human-made. And then we also have hydroelectric energy, so those are things like dams, which are using the stored water that is up higher to create electrical energy. And you may have heard something about the greenhouse effect and something about how burning fossil fuels can actually release CO2, and burning different things can release CO2. And you've heard of carbon dioxide, this greenhouse gas idea. And what the greenhouse gas effect is that the Earth is warmed by these gases that are present in the atmosphere. They are able to absorb and re-radiate heat energy, causing the Earth's atmosphere to warm and actually making it be a temperature that is pleasant. Without the greenhouse gas effect, Earth would not really be habitable. But the thing is, the more greenhouse gases you get, the greater the greenhouse gas effect is going to be, and so that enhances it and causes the Earth to warm. So sometimes when we're talking about energy sources, we consider, do they emit greenhouse gases or not? And you can see that on this little graph, we have some different greenhouse gases, and you can see that their presence in the atmosphere is really increasing. And this causes a change in the Earth's energy balance and a change in our climate. And that's something you've heard a lot about, and we're going to learn even more about that next year in IB Physics. So anytime we produce any type of energy to do anything, we always have energy that is lost, and we call this degraded energy. And it's turned into something that's not useful. So I try to get one type of energy out, I get some other energy as a result. And so the energy is being conserved, but the more you try and get it to do something, the more energy is going to be degraded, is going to be lost, and can't do anything useful anymore. We looked at this a couple units ago using Sankey diagrams. And so in a Sankey diagram, we have our total that we start with. So for instance, this is a Sankey diagram of combustion, taking gasoline and burning it to make some type of energy. And here we have a lot of energy that's lost for cooling, for exhaust, we have friction losses, and we only get 25% of our energy actually doing what we wanted it to. So for combustion, that might be driving our car. Sankey diagrams, as you recall, have arrows that tell us how much energy is being transferred in each different transfer that's happening, and how much we start with, how much we get out. In lots and lots of different power plants, you have some sort of hot area. It goes through some sort of process, sometimes spinning a turbine, and you have then some energy that goes to cold, and you only get out a little bit of that energy. So a Sankey diagram can help us think about how much energy we start with versus how much energy do we actually get out as the useful form of energy that particular process is going for, often electrical energy. From a Sankey diagram, we can determine the efficiency, which is the useful mechanical work done, or essentially the energy that we wanted to get, over the energy that we started with. So if we go back to the combustion engine, we had 100% energy coming in from combustion. We only got 25% energy out. So that means the efficiency of that engine would be 25%. Sankey diagrams can be pretty darn complicated. Here's one that is showing energy flow throughout the United States, where it starts, where it goes, what we use it for. But we're really noticing that the Sankey diagram is taking very complicated data and it's making it into a representation that lets us understand how it's flowing and moving and what different forms it's taking. So right now I'd like you to pause the video and practice using a Sankey diagram, two of them actually, to determine the efficiency of the two most common uses of thermal power plants. So you can pause, check. And you might have noticed that these power plants have efficiencies around 30%. So they're pretty inefficient, but that is about the maximum efficiency that we can get for combustion, for burning something. Other different types of electrical power plants can have higher efficiencies. Notably, hydroelectric power can be very efficient, and we'll learn more about that in a couple of days. But thinking about these different types of energy sources, what source do you think is most common in the whole wide world? Fossil fuels, you're right. Looking at this global energy consumption pie chart, we notice that oil is the most common, and then we are closely followed by coal and natural gas. So fossil fuels are taking up a very large portion of this pie. Looking more specifically at electricity production in the United States, you notice that coal is a large chunk of the pie, and you don't even see oil. Oil and natural gas aren't very often used for electricity production, although that's changing pretty slowly, but it is changing. And you notice that renewables are not a very large chunk of this pie. That is changing as well, and something that's going to be pretty relevant to your lives in the future. Today we're going to talk specifically about fossil fuels. So you've probably heard of them before, and fossil fuels are actually called fossil fuels because they're made of fossils, which is a little weird. But fossil fuels are dead and decaying stuff that has been covered by other rocks over top of the dead and decaying stuff, and trapped that dead and decaying stuff in between layers of rock. And in between layers of rock, you get really high pressures, which leads to higher temperatures, and sometimes some bacteria involved that causes a decomposition and actually a changing of the plant matter, the decaying animal and plant matter within there. And eventually, over millions and millions of years, you end up with some types of fossil fuels, which are oil and coal and natural gas. And the types actually depend on which types of plants and animals there were, what pressures and temperatures they experienced, all that jazz. And we can actually harness the energy that's contained within these fossil fuels by burning them to power steam engines. However, unfortunately, they're pretty big causes of atmospheric pollution and adding greenhouse gases to the atmosphere. So I'd like you right now to pause the video and actually go watch another video on how power plants work. Just a quick overview of what's going on. It's pretty helpful. I really like this video. And think about what types of energy transformations are involved in a coal power plant. Watch this short video. We'll go over it very quickly. We start with some type of chemical energy, and in this case it's a coal chemical energy, the energy within that coal, and we burn it through combustion, heating up water that is in these steam lines. So that water is heated up until it's steam, and the steam goes to turn the turbine, and the turbine is actually attached to this thing called a generator, which you've probably heard of before. But a generator is essentially just some coils of wire with some magnets, and either the wire or the magnets are spun or move, causing the production of electrical energy. So we get electrical energy out, and we actually have a fair bit of losses along the way, due to various inefficiencies. So we only get 35 units of our energy out. This whole process is very similar to what happens with other types of energy sources, nuclear reactors, sort of similar to wind, sort of similar to hydroelectric, sort of similar to some solar thermal, where we use some type of thermal energy to spin some turbine to generate some electrical energy using a generator. And for fossil fuels, there are some big pros and some big cons with this type of energy production. Fossil fuels are very cheap, especially currently, but in general, they're very, very cheap compared to other forms of electrical energy production. You get a high power output because they have a high energy density. We'll talk more about that in a second. And lots of things currently use them in the world, and we're really good at transporting it around and using it for all of our different ways of using electricity. There's a number of disadvantages, though. For example, we're going to run out pretty soon. In your lifetime, 50 to 100 years, the world will run out of fossil fuels to be able to use and burn. They also pollute the environment and, as you've heard of before, contribute to the greenhouse gas effect, releasing carbon dioxide into the Earth's atmosphere that ultimately changes the Earth's climate. And you've heard about that a lot lately. They're also really expensive to distribute because we get fossil fuels in one location, but then we want to go use them in another location, and they're very heavy. So you have to put in a lot of money into distributing them. And that distribution can cause some environmental problems. You've heard about the pipeline in North Dakota and the environmental problems that they're really concerned about there, because those are valid concerns that do happen and cause huge issues both environmentally and with the water supply, which is very important for life. So these fossil fuels, when they're mined, they actually tend to cause a lot of problems. They release toxic substances. When they're burned, they can also release toxic substances into the atmosphere like sulfur and heavy metals. And so when we're talking about pollution, there's two different kinds. There's this heavy metals and sulfur pollution that happens both in the mining process and in the burning process. And there's also the idea of greenhouse gases, which is a different type of pollution, but still pollution nonetheless. So thinking about these, we want to find out sometimes how much energy or how much stuff we need to be able to power something. So if I take my cell phone, for example, it needs about 20 kilojoules to be able to charge. And so if we wanted to charge my cell phone with a lump of coal, you want to think about, well, how much coal is that going to be? And to be able to figure that out, in IB physics, we're going to use two concepts. We're going to use specific energy, and that's the energy that you get from some amount of mass of that fuel. And it's measured in joules per kilogram. So for instance, coal has 30 megajoules, that's a lot, per kilogram. So if I have a kilogram of coal, it can release 30 megajoules of energy. Then it is going to go into a power plant that has some efficiency, and you'd have to consider that as well. But right now, we'll just think about this specific energy idea. And so again, it's the energy that's released during the combustion process. Energy density is another way we can look at that. Specific energy, you notice, is looking at megajoules per kilogram. Energy density is looking at the energy per volume. So it's going to look at megajoules per meters cubed or megajoules per liter. And you always want to make sure that when you're doing these problems, your units match up correctly. And these two ideas are very, very related. It just depends on what type of measurement tool you might be using. For coal, it's more likely you'd think about kilograms. For an oil or gas, it might be more likely that you'd think about a volume. I'd like you to pause for a moment and try and think about how much coal you would need to create 20 kilojoules of energy. We know that the specific energy of coal down here is 30 megajoules per kilogram. So pause and try and think about how you might calculate this. I calculated this by thinking about my specific energy as if it were an energy conversion, a unit conversion problem where I say, oh, I have this many joules and that equals 1 kilogram of coal. So if I take the amount of energy that I need and multiply it by this equivalent relationship, I can convert this amount of energy into how much coal I'm actually going to need, or 0.6 grams, not a ton. So as you're working on these problems, you have to think about them as factor label conversions. There are equations you could use, but that makes it a lot harder because we can just think about our specific energy and energy densities as equivalent relationships, just like 365 days is equal to 1 year. So when we're doing these problems, make sure you're showing this factor label conversion. Good luck, and keep physicsing.